Okay, thank you everyone for coming, and I apologize for not being able to attend the conference in person. I was a graduate at UC Santa Barbara, so I always wanted to give a talk, and I actually never given a talk at KITP, so I'm my first time, and unfortunately it's online, but I'm glad to have the opportunity to present to you virtually. So what I will be telling you about today, since there's a very diverse audience here, so let me tell you a little bit about our system, which is molecule, and then and a little bit of background before I get into our results. So we work with molecules. Okay, here. We work with molecules, and molecules have many quantum degrees of freedom, actually a hierarchy of energy scales, as shown here: electronic, vibration, rotation, and hyperfine degrees of freedom. And it's a pretty complex system, but in sort of the last 2 decades or so, we're now able to control a certain set of molecules completely. We can cool them, we can trap them, we can allow them to interact, we can probe them, we can even consider building up using these molecules as building blocks for more complicated systems. There is a variety of scientific directions for people in the ultra-cold molecules field are pursuing. They can be sort of generally grouped by sort of the number of body involved in terms of the relevant physics. Single body physics for precision measurement, search for new physics, to or many body physics concerning using these molecules for quantum science application, novel face on matters or quantum computing. And what I will be telling you today about is sort of this to few body physics, where we this topic in relevant to the conference today is the ultra-cold chemistry and collisions. Before I tell you about our specific result, I want to give just a couple examples, and of course there is a lot, it's a very active field, so there's a lot of examples, but I'm just picking a couple here to give some general ideas. People can now, for example, study collisions of co-propagating atoms and molecule with their collision energy tuned, for example, shown on this axis, and measure their collisional cross-sections. And this can be compared to quantum chemistry calculation. Basically, you can put the geometry of these atoms in their distance, or so on and so forth, into these quantum chemistry package, or something a little bit more sophisticated, beyond package, and calculate, the underlying potential and then the scattering involving with such a system, and calculate what the collisional cross section is, and compare the experimental data with that. And in this work, they found that they had to include a lot of electronic correlations to be able to have accurate sort of predictions matching the experimental data. One can also synthesize quite exotic chemical species, such as the one shown here. What I will be telling you about is this example here, where we can probe the transformation of chemical reactions from starting with reactants to all the way to reaction products, but also seeing the reaction intermediates. And this actually is a series of work to sort of bring to this understanding of such a transformation. And this all started with the work back in July in Debbie Jing and Jing Yi's group back in the early, I would say, starting in the early 2000, and really sort of have the first result in around 2008, where I was also a graduate student. So back then, the first sort of high density and high phase space density gas of molecule. These molecules are made out of alkali atoms, of two different species of alkali atoms, or created, trapped, and these molecules are totally controlled in a single hyperfine rotation vibration electronic ground state. This is a picture of such a gas that we can take absorption imaging of. what was real surprise once these molecules were created at this very cold temperature and dense, high density, so overall high phase space density, they were lost via two-body process that was evident in this data set. So this was already the lowest energy states of that particular molecule. So what could happen? And sort of right away, people thought about chemical reactions. So they collide, and then they can undergo chemical reactions, and therefore the end result is a different species of molecule that we can no longer see. That's why we see these two-body loss. And there was a lot of sort of study on looking at this loss. Let me just describe the process a little bit, starting with reactants that prepare, precisely and at this sort of reaction coordinate. They can get close through long-range forces, and that can be varied, and that's sort of the topic of a lot of these references here. They can have barrier, they can have angular momentum barriers, and they're usually pretty shallow, so these very cold gas can still tunnel through to get into the short range where this potential could be very, very deep. And this is where chemistry can happen and then result into reaction products. But the experiment at the time had no means of measuring what actually happened here, because everything relies on measuring the reactant. So we can, at the time, only see the reaction loss and then infer things from there. Learned a lot of things already in terms of the long-range physics, but not much was known about what actually happened down here. So we need a direct detection methods to really see what actually happened here. So this is what we set out to do at Harvard. Actually 8 years ago or 9 years ago now, we set out to combine tools from both atomic molecular physics to prepare these quantum state specific reactants, and combine with physical chemistry tool ion detectors to be able to probe such a reaction in a more general way. So specifically, we want to probe via ion spectrometry. So all the experiments started out with, for example, on the order of 10,000 molecules that we created using AMO techniques. And these molecules are relatively cold, hundreds of nanokelvin. And we can insert, basically surrounded this cloud, we had these a set of ion, these electric field plates that we can subsequently ionize via lasers of these, whatever is in this trap, and then detect on our detector. And we will get information such as the species through its mass information, time of flight mass information, and the spatial distribution. So these electric field plates are arranged in such a way that they map kinetic energy onto the same kinetic energy onto different rings. So we can also, from the spatial distribution, get information on the kinetic energy. And we can repeat in a single experimental cycle doing these ionization many times, thousands of times, to accumulate for statistics. So once these experiments these apparatus were put together and functioning, well, we sort of have our first result, which was to use mass spec to indeed saw that these directly measure these chemical reaction products of potassium dimer and rubidium dimer. So these are the peaks that show up here. So we were very excited. Finally, we have a ways to directly detect what actually happened in the initial gas, where we can only see loss of KRB, and now we see indeed these chemical reaction product forms. We can, utilizing this spatial distribution capability to gain kinetic energy information to verify these reactions, these potassium dimer, rubidium dimers are indeed the products. For example, KRB molecules that we start out with, the reactant is very cold, so it just shows up as a dot on our detector, which we can blow out to have, this is more or less our resolution limit. For K2 and RB2 that we ionize, these are reaction products. They actually has a larger size, okay, so larger size compared to the initial reactants, and they have the sort of the size ratio, which can be understood as to their momentum ratio. Basically, these chemical reaction occur, then potassium dimer, rubidium dimer forms, they fly away with equal but opposite momentum, and they show up on our detector, and then tell, from there we are able to verify that these ions are indeed coming from the reactions due to these momentum conservation tricks. Okay, so this was actually, in some sense, surprising, certainly surprising from 10 years ago when we first saw that there's chemical reaction, there could be hints of chemical reaction, and now we have the direct measurement. But this was not the only thing that we saw. So this is the same plot that I already showed you. We ionize at a specific wavelength just to be able to ionize, these gas. If we change the wavelength, so from 305 to 335, what we saw is some other peaks. Some peaks still remain, some other peaks shows up, in particular sort of the 4-atom peaks and the 3-atom peaks. And it turns out through some more detailed work, we realize that these are all coming from the same source, which is this chemical reaction complex. So either through direct ionization or dissociated ionization process. So this was actually very surprising, because the chemical reaction intermediate usually is very transient in nature. It's, it only spans a short amount of time. Typical chemical reaction maybe it lives on the order of picoseconds, and our pulses are coming in, pulse durations are on the order of nanosecond. So we didn't, expect to see them at first. But if we scrutinize what's actually happened using this potential energy landscape, then we can begin to understand what's going on. So before I show you, it was all sort of cartoon, but here now it has some real numbers. So this chemical reaction is, energetically allowed with very small amount of energy. So in chemistry, people like to use wave number, 10 wave number, and translate to temperature. This will be 10 Kelvin, roughly 10 Kelvin. So wave number is about a Kelvin. And it has to go through a very deep well. The complex is actually highly vibrationally excited with thousands, a couple of thousands of Kelvin worth of energy. And while this chemical reaction traversed from left to right, it actually sort of, in some sense, you can think of as a bee trapped in a bottle and couldn't find this opening. So it actually sort of, trapped inside here for a very long time before it can find, quantum channel to come out. And this can be scrutinized, and the time scale can actually also be estimated. And then I think in sort of different fields, they have different, basically similar physics. It's the same physics, but different with the name. So in chemistry, it's called RRKM, named after these 4 scientists, where these complex lifetime is equal to h times the density of state. So higher density of state has longer complex lifetime, divided by the number of open channels that's the product, or the different ways that these things can come out. So then the test is to calculate, with this simple formula, the test is to calculate what is the density of state. And it turns out to be kind of tricky. So there are different numbers, but nevertheless, they are quite long. You can see they're on the order of microseconds. And experimentally, the fact that we already seen it without knowing exactly the ionization cross-section also put us to these complex lifetime at this microsecond time scale. So then in some sense, it's not surprising after we actually put all the numbers together, but it's very intriguing. So what we are interested to do is to do a direct measurement of this lifetime, so not just infer. The tricky thing is that the time scale for these collision to happen are on the orders of the seconds to get to this complex, and then the complex dissociation into product will be on the order of microsecond, or hundreds of nanoseconds. So to initiate this zero is very difficult, but it turns out it's very interesting that we trap these molecule, and that molecule initially trapped here, that light can actually interact with that very fast flashlight can interact with the complex and deplete that, and so give us a very nice initialization of t equal to 0. So once we sort of clean out this population with that light, we can turn that off and then see that watching this intermediate complex building up, and we get a direct measurement of the time scale of this lifetime being 360 nanoseconds. And this actually compares favorable to one of the theoretical calculation, and only different by a factor of 2 using this very simple sort of RRKM assumption. So this was really interesting, and we're happy to directly see it and actually match with simple calculations. And this is kind of what I have sort of want to orient us, is that after we see these these chemical reactions, see these reaction complex, what the main topic that I want to discuss today is to sort of do this precision test to completely characterize where the energy go, the reaction products, and then compare that to statistical theory. And then at the end, there are surprises where things actually don't always make sense or still remain sort of mystery. So now, a goal of the experiment is to really be able to characterize such a chemical reaction process completely quantum mechanically, which means we want to to prepare a potential energy surface describing the reaction, to do scattering calculation on top of it, and then be able to predict what happened, where the reaction products will go in turns out into the specific quantum state channels. It turns out even with just 4 atoms, but of course for very heavy atom, that this is beyond the state of the art of the theory to do such a calculation. But the fact that we observe such a long-lived complex would suggest we can compare to a theory based on statistical product distribution, namely that let's just say there's no anything completely chaotic process going on in this complex. Explore phase-based very thoroughly, such that any possible outcome channels are equally likely to be populated. Okay, so that's the statistical part that we can compare to in the absence of a state-of-the-art theory, and we can see how well that comparison does. Okay, so to do that, we need to detect the chemical to detect the quantum state of the products, which I haven't shown. First, we need to know what is the possible product, and with 10 wave number or 10 Kelvin worth of energy, that turns out to give no vibration excitation, energetically forbidden, not enough energy, but the molecule can rotate, so the excitation can come into sort of forms of rotation, so it can go up to relatively high quantum number, but still sort of manageable, we hope. So to detect these reaction product in this quantum state, we use a technique called resonant enhanced multiphoton ionization. And the idea is just to drive a 2-photon process. The first photon tells us the quantum state, and then make the transition, and then the second photon ionize the product, and therefore whatever register on our detectors are the ones that in a specific quantum state. So that way we get the state information. And when we did that and go through all the possible rotation state, we were able to accumulate data to show right here potassium dimer, rubidium dimer, and you'll see that interestingly, these rotation quantum numbers are, they're even in our preference. And this actually tells us something about the nuclear spin. And the reason it tells us something about the nuclear spin is because these molecules are homonuclear molecules. So therefore, these molecules have the same nuclei, so indistinguishable nuclei, and they have to respect exchange symmetry of the nuclei. So turns out for potassium molecule, the nuclei are boson, and therefore, if the nuclear spin is conserved, let's say starting with a symmetric wave function pointing in the same direction, then the rotation wave function have to also be symmetric, and that's what you see: 0, 2, 4, 6, 8, 10, 12. And then for rubidium nuclei, it turns out to be fermionic, and therefore, again, symmetric wave function, spin wave function imply that the rotation wave function has to be anti-symmetric, and then that's what we see 1, 3, 5, 7, 9, so on and so forth. So this was kind of an interesting measurement that tell us in such a chemical reaction, nuclear spin actually is conserved, and then we have these nice measurements telling us, from the correlation of spin and rotation to tell us that. Okay, so but in order to get these reaction product distribution, we need more information. We need to resolve these products not just in this accumulated way. We need to know them from a single event. So can we do that? To do that, we need to have additional information. So we need to apply these coincident detection technique, where we need to ionize the potassium dimer and the rubidium dimer, the products, simultaneously, and register on our detector to know that they come from the same reaction event. Okay, so to do that, we ionize this then in particular state simultaneously, and then apply these momentum conservation constraint onto our data. So these products are correlated, they're from the same event, they have to carry equal and opposite momentum in all x, y, z direction. And that's an information that we can get from our detector to both the time of flight axis and also for the x and y axis, where we have the momentum information directly. So applying these filters, we're able to screen out and eliminate things that are not from the same event, just a coincident count, and leave behind, just leave with us the coincident detection. Now we're able to detect, screen out the information from the products from the same events, and then we can now look at all the possible outcomes. But before we do that, we need to have a statistical distribution to compare to. And in our reactions, this is the outcome. The outcome is potassium dimer, rubidium dimer. We measure its rotation states, but there's one angular momentum that we don't actually measure, which is the orbital angular momentum when these molecules fly apart from one another. So that actually becomes a degeneracy factor, because there's many different ways adding 3 vectors. Knowing 2 of them could add up to 1, which is the initial total angular momentum. So these are the numbers that's specified here, for potassium dimer to be, say, 12 and rubidium dimer to be 7. There are 23 different ways of adding these 3 angular momentum together to be 1. Okay, so that means that if the statistical theory holds, then we do expect to see more population ended up in these states, because there's more microstates. Okay, so now we are able to go into, there are actually 57 possibility. So we go into 57 possibility to sit there, accumulate data, and overall we accumulate data for about 3 months individually and collectively, and then and this is what we get. And you can see that we do have more population kind of at the corner where there is large number, but smaller difference between the 2 quantum numbers. We can compare them fully, and we do that in this paper. But let me just take one cut in this particular cut. For example, potassium dimer in K2 equal to A, and we can compare the statistical model, so just counting the number of states, to our measurement, and you can see that everything matched pretty well except for 1 channel. Okay, so it turns out there are 7 channels out of 57 channels that are sort of deviating statistically significantly. But if we remove them, using likelihood ratio, then we can say our data match the statistical counting well. So I would say this, so first order, this very long-lived complex lifetime tell us, statistical model does pretty well. But if we have a very precise measurement like the ones that we do, we can pinpoint a specific quantum state where that deviate from the statistical model. However, we don't really know why, because we don't have a quantum calculation, or we don't have sort of the next level of sophistication to give us a reason. One of the channels that we actually do know the reason, but I can mention that in the discussion if anyone is interested. But this is what we know, and this is sort of the result of our very precise measurement.
It's
Okay.
still 5 minutes to go.
Yeah, sounds good. So now, what's next? Next, we are interested in working with a system that is calculation-wise more tractable. So atom molecule collision, atom molecule reactions, where there's only 3 atoms involved. Okay, so in particular, we pick KRB plus rubidium reaction collision, and this is the potential energy landscape for that. So KRB plus rubidium collide, but it cannot energetically goes to K plus RB2, so it should just go back to KRB plus RB. But it does have, again, this very deep potential wells, sort of thousands of kelvins deep. So complex is expected. Okay, so complex is expected, and perhaps photo excitation of complex is also possible, as I didn't mention too much, but that's a way to clean out this complex to start from 0 and start from t equal to 0. That was the measurement that we've done before. And then we can also go to KRB plus potassium reaction, which is energetically allowed. So that's something that will also be interesting to study. Okay, so the first thing we can do is to investigate these complex, which we have shown that, we have a good understanding for the molecular case. So KRB plus molecule, we had made the measurement and then matched well to the RRKM prediction. And at the same time, there was a different system that was done, rubidium cesium, using a different method to measure that they also came very close to the prediction. Okay. So that's a good starting point. For KRB plus RB, we do expect to be a very short complex lifetime, because in this case, the density of state is much less, or the rho here is much less, and therefore it could be challenging to see. But nevertheless, we went ahead, and what was actually quite surprising was that we measure this complex lifetime to be actually extremely long, even longer than the molecule-molecule case. Actually different by a factor of 10 to the 5. So 5 orders of magnitude different compared to this predictions, or just this sort of simple RRKM argument. And at the same time, there are other systems, other molecule systems that have made measurements, although indirect, but they, on the sun assumption, they also see much longer lifetime compared to the prediction of RRKM. So this is not understood. So what could be happening? Well, it could be this RRKM assumption is not valid for this system. The density of states is assumed to be very large, but in our case, it's much less compared to the temperature spread, and therefore not a good assumption. But one would expect the chance of actually hitting a resonance and therefore result into a very large complex lifetime to be very low. So, are we lucky to hit it, or is there something else going on? So this could be breaking down with this assumption, or that this holds, but the way we count the states is incorrect. Angular momentum is not fully conserved in this case. And here's calculations showing if they're not conserved, so in the presence of a small electric field, which we have very small electric field, 17 volts per centimeter. So we think it should be conserved, but okay, if it's not conserved, then perhaps there could be, several orders of magnitude of miscounting, or one has to count to that. That could be another possibility, but we don't really know. Yeah. Okay, so let me just summarize. So we brought these tools together, physics and chemistry tools together, to completely characterize molecule-molecule reactive process with full state-to-state detail. we now turn our attention to something that we thought would be more tractable, so that theory, could give us more information, but it turns out to be even more surprising. So order of magnitude too long, complex lifetime, and we're beginning to investigate, these collisions of atom molecule in the presence of at different magnetic field to see whether there are some features, and depends on the spin states, we found either complete loss compared to no atoms, or we see some very broad features. This is preliminary data. Okay, with that, I want to close out by thanking for your attention and thank the members of my team who work on this. A lot of the results that I show you were done by the people who are now move on to their their next position. Currently in the group we have 3 members, Yixiang Liu and Mark Babin and Lin Bangzu on the team. Yeah. Okay, so I'll stop here and take any questions.
Very much for this very interesting talk. Now we have some questions. The first one is there.
I'm curious about your nuclear spin alternation. Can you go back to that slide?
Yeah, absolutely. Let me just go look for it real quick.
Yeah. So if spin is 0, yes, the odd numbers are missing. But if spin is, you said in rubidium-2 the spin is 3/2, or?
Yes. So the spin is, yes, the spin,
Yeah.
the
So
rubidium-2
well, according to theory, intensity alternation should be 5:3, and you have missing. So you shouldn't have missing even levels. Although it is a fermion is correct, but the intensity alternation should be 5:3.
I guess I don't really understand that language. So my understanding is that these rubidium nuclei are fermions, so they have to respect exchange symmetry, and we start with a specific spin in the reactants, and that's just say they're both pointing up in the blue balls, and then after reaction they are in the same orientation, so it's a symmetric spin wave function, and therefore the overall exchange still has to have a minus sign, and that has to come from the orbital part, and the orbital part is the rotation part, and therefore it's all the odd numbers are allowed. I mean, all the odd numbers which is energetically allowed are allowed.
Yeah. But if you will take rubidium-2 just in bulb, there will be alternation of 5:3.
What is the alternation of 5:3?
Yeah, it's statistical mixture. So it's not a statistical mixture.
Right, it's not a statistical mixture. It is starting in a specific quantum state, like say they're all pointing up in one particular hyperfine state, and then after the reaction.
Yeah. No, it was just your explanation. You said it's fermion, and therefore it is missing, like even levels are missing, but it's more than that.
Okay. I mean, they're fermion, they're indistinguishable fermion, so.
The small red in the rubidium case is a measure of the error or contamination or.
Yeah. So it turns out that's a very good observation. So it turns out, so let me look for this this slide real quick. Let me quickly. So it turns out this. The spin preparation that we start out with, that quantum number is good in at large magnetic field. So at different magnetic field, let's see if I have that. So I guess it's not contamination. It's well understood. I'm just trying to see the data. Okay, so let me share. So it turns out these odd events depends on how the initial spin is prepared, and then through the spin conservation, if you start with superposition of states, then the end result could be admixture of spin symmetric, spin anti-symmetric state, and that could be tuned by magnetic field. And in that case, what I shown you was 30 Gauss. There is a small amount of possibility of anti-symmetric because of the initial preparation of the state is in actually a superposition, a small admixture of a state that can end up in the anti-symmetric state. So it's everything still holds. It's just that unless we're at a very, very high magnetic field, these spin projections are, these bases are not the good bases.
Questions? Yes, one there.
Okay, Kang-Kuen, if I remember correctly,
Yeah.
from 2010 experiments, the rubidium plus KRB reaction or loss of molecules in that collision, if you prepared both rubidium and KRB in its lowest hyperfine state, it was consistent with zero loss. But if either rubidium or KRB were prepared in an excited hyperfine state, it was consistent with universal van der Waals loss. Do you do you have any insights about that yet from anything you've done there, or any thoughts?
Yeah. So
what's going on?
Right. So that we're just beginning to sort of look into that again. So just one sec. So I'm not showing you. So basically that is still more or less consistent of what we've seen. So I'm only showing you here the complex, but this KRB is not in the lowest energy states. The KRB is not in the lowest hyperfine states. And we do see, and then after they collide, they form complex. The surprising thing is that complex live for a very long time. So it's initiated from the collision of atom and molecule to get into the complex. Now with the different spin combination, the lowest hyperfine state of KRB plus rubidium, we do still see complex, but these were done at much lower magnetic field, because that's where we can detect with ion, so that the ion doesn't miss our target due to Lorentz force. And at those low magnetic field, we do also see more or less universal loss for the lowest hyperfine state of KRB plus RB. So we don't really understand why that is the case. So we're studying that, and then one of the things I do, we do see here. So this is kind of referring, maybe I should have showed this better. So this is the combination that we steer up into. So this is where we see universal loss, and we see universal loss sort of across all magnetic field. And this is the combination where we don't see universal loss at near Feshbach field, but we do see subsequently, if they're at a different magnetic field, the loss could be faster, or could be closer to universal loss. So why it's like this? We had this nice data, but preliminary, we don't really understand. So I don't know, Paul, if you have any insight.
No, it was a real puzzle. We didn't understand it then. We don't understand it now.
Well, we now have more tools. So what we want to do is to probe with the complex. We probe the complex at different field. For this combination, they're all about the same order of magnitude, super long. We probe the complex here at low field, it's super long. We haven't had a chance to probe at high field. We need to, do something about it because of the large Lorentz force. So we're going to have to correct for the ion trajectory. But we want to probe up here where it's non-universal, so it's different, at least, to see whether the complex lifetime is different there. Yeah.
Kang-Kuen, I was wondering if you could comment on the status of understanding, I guess there are trapping fields on during the chemical reaction, and how does that affect your measurement and the Gilla measurement?
Yeah, so I would say all the measurement usually we've done in the absence of the trapping field, because in the presence of the trapping field, then these complexes are mostly photoexcited, and it doesn't. A small portion goes to the chemical reaction product, but that's a small part. So all the experiment we've done are sort of, we do this chopping. Let's see, we do these chopping modulated of ODT. So we probe it in the dark in some sense. So I would say in the July experiment, they are mostly photoexcited complexes is the result of their loss. Is the dominant source of loss, not the reaction products.
I see. Thanks.
Yeah.
Hi. On your last slide, you flashed a paper where you said, okay, that could be an explanation. If angular momentum is not conserved, then that could explain this longer lifetime of your complex. But you didn't spend a lot of time on that. Perhaps you can explain a little bit more how this works, the physics behind it.
Yeah, so that's a very good question, and I don't know as much detail as I like. So basically, it's somehow count the number of states that one counts here. So basically, if the angular momentum is not conserved, the number of states that one counts here, the density of states, is very different, and therefore that goes into this numerator. I mean, that's sort of the extent. Then there's a lot of study on that. There's a lot of sort of theoretical paper on that. Is all I can say. But I would say we don't know whether these angular moment, whether these conservation holds or not holds. We know in the case of KRB they hold, because we checked it with, even nucleus is conserved. So everything is conserved, like in the KRB plus KRB case. But in the K plus KRB case, they may not be conserved. We don't know. We would like to be able to check it experimentally. The one difference is that KRB plus RB, the rubidium has an electron spin. So one can imagine that maybe couple more strongly.
Isn't there also angular momentum in the separating fragments? Or are you just counting the angular momentum in the molecules?
Right. So in this case, there's only one channel because it's energetically forbidden to go out. So there's only one channel to go over here. So if its angular momentum is not conserved, then there is energetically only a few channels, I would say. While inside here in the complex, there could be dramatically more, as shown in this paper. Yeah.
More questions? I have a curiosity about calculations. So you said that for molecule, it's more or less impossible. For atom-molecule, there are calculations. And you show at the beginning calculation atom-atom, which were very, very sophisticated. I think it was couple cluster with quartet and so on.
Right.
And what kind of calculations are for the atom molecule?
I think similar, just because there's one less atom, so the dimensionality of the problem is much reduced. And in that case, I believe the potential energy surface exists, can be calculated for KRB plus RB using these quantum chemistry calculations. So people like Svetlana Korochkova, or people like yeah, I mean that I think it's using similar kind of quantum chemistry package type of calculation as a starting point.
Thank you.
Yeah, thanks.
If there are no more questions, Then we thank again. And
Thank you.